Welcome to this explainer. I'm really excited to dive into a topic today that is absolutely fascinating, but honestly, kind of overlooked in industrial plant design. When we think about power distribution, we're usually obsessing over the cables themselves, right? The gauge, the insulation, the routing. But today, we're going to flip that entirely. We're zooming in on the structural foundations holding those cables, specifically how the actual physical geometry of your cable trays directly impacts ampacity. Let's get right into it.
So here's a provocative question for you. Could your tray geometry literally be choking your plant's power? I know, it sounds a bit counterintuitive. We tend to think of these as just passive metal trays holding up wires, right? How could they possibly threaten plant efficiency? Well, as we're going to see, the physical shape of the tray you select interacts directly with the physical laws of electricity. Pick the wrong geometry for your environment, and you might accidentally be suffocating your electrical system before you even flip a switch.
Here's how we're going to break this down today. First, the cable tray triad. Then, how geometry dictates ampacity. Third, the intersecting variables. Fourth, we'll look at the 9-parameter decision matrix. And finally, we'll wrap up with Xinma standards.
All right, part 1, the cable tray triad.
Now, you're likely familiar with the big three: the ladder tray, the perforated tray, and the solid bottom tray. But here is the critical thing. They're absolutely not interchangeable. Swapping one for another isn't just an aesthetic choice, it's a make-or-break engineering decision. What works perfectly in a main power corridor is going to be entirely wrong and honestly potentially dangerous if you try to use it in, say, a chemical spray zone or a sensitive control room.
Let's move to part 2. Geometry dictates ampacity.
This right here illustrates that hidden danger we just talked about. Look at the ampacity derating percentage under full load. As a quick refresher, ampacity is just the maximum continuous current a conductor can handle without exceeding its temperature rating. Now, an open ladder tray, you're looking at a minimal derating, maybe up to 10% max. But check out the solid bottom tray. We are talking about a massive derating penalty of up to 30%. That means the exact same cable carries significantly less power, all because of the shape of the metal resting right beneath it.
It really all comes down to thermodynamics. The open ladder design physically promotes airflow. It lets the heat generated by the electrical current dissipate naturally, kind of like a cool breeze on a hot engine, which keeps that ampacity derating as close to zero as possible. On the flip side, a solid bottom tray acts like you're wrapping your cables in a heavy winter coat while they're sitting in a sauna. It literally traps the thermal energy. And you know what happens then? That trapped heat increases the resistance within the cables, severely lowering their capacity to carry current safely. That's exactly what triggers that massive 20 to 30% derating penalty.
Which brings us to section 3, the intersecting variables.
So that begs a pretty logical question. If ladder trays are just so incredibly efficient electrically, why on earth wouldn't we just use them everywhere and completely avoid derating? Seems like a no-brainer, right? Well, the reality of field engineering is that electrical efficiency is just one piece of a much larger, much more complex puzzle.
To figure this out, you have to run through a mandatory checking sequence. Step 1 is support span. Step 2 is load class. And Step 3 is contamination. You absolutely cannot just optimize for electrical ampacity without checking these 3 variables first. For example, sure, you might really want an open ladder tray to get that maximum airflow, but what if your cable route goes right through a zone with heavy chemical dripping, or maybe a lot of airborne dust? Suddenly, that contamination factor makes an open ladder a terrible choice. You'd be forced to reconsider your geometry and recalculate your ampacity based on a much more enclosed protective tray.
All right, section 4, the 9-parameter decision matrix. This matrix is basically your cheat sheet. It shows you exactly how to systematically match your tray types to specific plant environments based on those intersecting parameters. Take a main pipe rack, for instance. There, you're going to heavily favor the ladder tray, so you can maximize your ampacity and span safely over long distances. But if you move down to a hazardous zone or a process area, things change fast. Suddenly, you see avoid or check first for ladders, pushing you toward perforated or solid bottom trays to handle specific environmental contamination or load conditions. It's a constant, tricky balancing act between getting the structural protection you need and maintaining your electrical efficiency.
Finally, section 5. Xinma standards.
When it actually comes to executing these matrix decisions out in the real world, Shanghai, Xinma, Busway, and Cable Tray is a massive authority. They offer a huge suite of solutions, everything from your standard tray systems to advanced busways, seismic bracing, and even intelligent cable management.
and they apply these exact geometry-based ampacity calculations across incredibly diverse projects. We're talking keeping power flowing safely in everything from super high-heat data centers to rail transit and massive industrial plants.
But the absolutely essential piece here is compliance. Look, whether you're dealing with a 0% derating open ladder or a 30% derating solid bottom tray, the physical construction has to meet rigorous international standards. Otherwise, all those theoretical load and thermal calculations are basically useless. Products that are engineered to IEC 61537, NEMA VE1, BSEN 50085, and GB 31251. They guarantee that your tray geometry isn't just going to support the physical weight, but will reliably perform electrically exactly as you expect it to over the entire lifespan of your plant.
Well, we have covered a lot of ground today, from the basic triad of trays to the really profound impact that a tray's physical geometry has on electrical ampacity and heat dissipation. So I want to leave you with this one final crucial thought. You've undoubtedly checked your cables, but have you checked what's holding them? The next time you walk through a facility, just look up. That metal framework isn't just structural support. It is an active participant in your plant's electrical efficiency. Thanks so much for joining me for this explainer, and definitely keep asking those critical questions.